5.180. A quartz plate cut parallel to the optical axis and placed between two crossed Nicol prism. The angle between principal direction of Nicol prism and the plate is equals to 45 degree. The thickness of the plate D, this thickness is given as 0.50 millimeter. Okay. At what wavelength in the interval from lambda 0.50 to 0.60 micrometer, the intensity of light which passes through the system is independent of rotation of the rear prism. The difference of refractive indices for ordinary and extraordinary rays in the wavelength interval delta n is equals to 0.0090. So basically there is a quartz plate, it is placed between two Nicol prism, right? Rays coming like this. Now we have to find out wavelengths between this range that is independent of rotation of this rear prism. Okay. So basically in a quartz plate, when it is cut through perpendicular to its optical axis, right, then incident light normally, if it is entering incident light at its face perpendicular to the surface, then it gets divided in two parts. One is ordinary ray and second one is extraordinary ray. These two rays moves in same direction, but there is difference in velocity. So if two rays are moving from this quartz crystal, right, one is ordinary and another is extraordinary, right, with different velocities, then definitely there will be a phase difference. Okay, that phase difference delta can be expressed as 2 pi over lambda into Ne minus No, where it is refractive index Ne for a extraordinary ray and No for ordinary ray, into D, where D is thickness of this quartz, right? So in this expression, this delta N is given as 0.0090. So we can write delta equals to 2 pi over lambda into 0.0090, the difference of refractive index, and thickness 0.50 into 10 to power minus 3. Okay, so from here we'll get delta equals to 9 pi lambda in micrometers. Basically here we just need to adjust the powers, right? Or let me show the calculation. We can write it as 0.9 into 10 to power minus 2 into 5 into 10 to power minus 4 into 2 divided by lambda and pi. So we'll get 9 pi over lambda. Okay. So if we'll take this lower wavelength, okay, 0.50. So from there we'll get delta is equals to, if we'll take 0.50, then we'll get 18 pi. Right. And this delta would, independent of rotation of your rear prism, when it is k plus 1 by 2 pi, which is in this range, okay, for 0.50 to 0.60, right? So we can choose value of k that can be 15, 16 or 17 to limit our phase difference between the range of wavelengths 0.50, 0.60, right? And now if we'll substitute one by one in this relation, for k equals to 15. First put k equals to 15 and calculate delta. So if we'll put k equals to 15, then delta is equals to 15 plus 1 by 2 into pi. That is 31 upon 2 pi. And put in this equation and calculate lambda. So for 15 we'll get 31 upon 2 pi is equals to 9 pi over lambda. So from there we'll get lambda equals to 0.54143 micrometer. Similarly, we can calculate for 16 and 17. So for 16 we'll get 0.5435 and for 17 we'll get 0.5806 micrometer. So basically we'll get three wavelengths in range of 0.50 to 0.60, where there will be no effect on extraordinary and ordinary ray due to rotation of rear Nicol bridge.